So now we're going to move into the turbomachinery section of the course. Still working in the context of conservation of energy, turbomachines are rotating machines that either add or remove energy from the system through shaft work. So pumps and fans add energy to the fluid, and turbines extract energy from the fluid. So most of these types of things are connected to a rotating shaft of some kind, and that's where the term turbomachinery comes from. But they're really work transfer devices, either adding or removing work to the system. Therefore, they impact conservation of energy for the system. So let's just recap a little bit about what we know about conservation of energy in piping systems. Well, we started off doing that by looking at Bernoulli's equation. And Bernoulli's equation is a conservation of energy equation, but there are many, many assumptions built into it. So starting off with basic Bernoulli's equation, which we see here, remember that the P term here actually represents enthalpy, and then this is kinetic energy and potential energy. So Bernoulli's equation says that the sum of those three things remains constant as we go from location 1 to location 2 along a streamline, or from location 1 to location 2 along our piping system. Now, that equation doesn't allow for any losses. So we've been modifying that equation in recent weeks to bring back in losses, and now we're going to bring back in the possibility of shaft work as well in the form of a turbomachine. So the first modification we made to Bernoulli's equation was we added a loss term on the right-hand side. So plus delta PL represents the pressure losses in the piping system due to pipe friction and minor losses. So that's a way of undoing one of the assumptions in Bernoulli's equation. Basic Bernoulli's equation is for inviscid flow, no viscous losses at all. We fix that assumption by putting delta PL on the right-hand side. And in the last few weeks, we've been talking a lot about how to calculate that. Now we want to further modify this equation by allowing turbomachinery to be introduced. So first of all, if we're adding a pump or a fan to the system, then we would have a minus delta P pump here. Remember, a pump or a fan is an energy input into the system, so that would be a minus on the right-hand side of the equation. And alternatively, if we're adding a turbine in, that would show up on the right-hand side as plus delta P turbine. So again, a turbine extracts energy from the fluid, so it would be an additive term on the right-hand side of this equation. So these terms just show the modifications that are required to the basic Bernoulli's equation to account for energy losses, energy inputs by a pump, or energy being extracted by a turbine. So we want to start off by just looking at pump classification. What are all the different types of pumps out there, and where do they work best, and when should they be selected? So first of all, we're going to divide them into two major categories: positive displacement pumps and dynamic pumps. Positive displacement pumps could be either reciprocating pumps or rotating pumps. So the rotating pumps would be classified as turbomachines, and the reciprocating pumps not, but they still have the same basic operation in many cases. Dynamic pumps can be further categorized into two types: centrifugal pumps, also known as radial flow pumps, and axial flow pumps. Now, in reality, many of these pumps are a bit of a blend between the two of these, but the primary direction of flow through them relative to the rotating axis is what's being used here to classify them. If the flow is primarily in the radial direction, so away from the axis of rotation towards the periphery, that's a radial flow or centrifugal pump. But if the flow is primarily along the axis, then that's called an axial flow pump. And we'll talk more about those as we go forward. So first of all, just some characteristics of positive displacement pumps. We're not going to spend a lot of time on positive displacement pumps after this brief introduction, but they are quite common, and so we want to know a few things about them at least. So in a positive displacement pump, the fluid is forced to a higher pressure by direct mechanical displacement. To accomplish this, the fluid is in a trapped volume of some sort, and then there's a mechanism in that volume that pushes that fluid to a higher pressure location. And we'll see this when we look at examples of them in a few moments here. Another characteristic of positive displacement pumps is that very high pressures are possible, but along with that, generally they have quite low flow rates. So we'll see as we look at different types of pumps that these two characteristics, the pressure they can achieve and the flow rate that they can achieve, generally go hand in hand in that as one goes up, the other goes down. So a pump that is good at providing very, very high pressures typically only provides low flow rates, whereas a pump that can provide very high flow rates typically can only provide moderate or low pressure increases. And we'll see why that is when we get into it a little more here. Now, another characteristic of positive displacement pumps is that they typically require pressure relief at their exit. So because they have a trapped volume of fluid, which they're directly displacing into a higher pressure region, if there's nowhere for that fluid to go, then the pressure will go very, very high very quickly. So they typically have some kind of pressure relief at their exit. So let's just take a look at a bunch of different positive displacement pumps, and you can see a lot of these characteristics that we've been talking about in action. So this first one is a reciprocating plunger pump, and this is a very simple style of pump. We have a chamber here. The flow is from left to right, so coming in the suction pipe and out the discharge pipe. The volume of this chamber is changed simply by having this shaft, this plunger, moving up and down. So when the plunger moves up in this direction, then the volume of the chamber effectively is larger and fluid is drawn in through the suction valve. And then when the plunger moves downwards, the volume of the chamber is effectively smaller and the fluid is forced out the discharge valve. So the positive displacement is being achieved by this plunger moving up and down. So there's a direct mechanical force being applied on the fluid to move it up to higher pressure. So you can see the problem here if this discharge pipe is closed. So if there's a valve down here or something and it's completely closed off and this plunger moves down, there's simply nowhere for that fluid to go. And if it's an incompressible fluid, that means that its pressure will increase very, very rapidly and something has to give. Either the motor or whatever that is providing this motion will not be powerful enough to make it happen, or something's going to break. So we typically need pressure relief on the discharge of these pumps so that they're not damaged. The next style of positive displacement pump is a gear pump. And these are very common in hydraulic systems, so lifts and front-end loaders and backhoes and that sort of thing. So again, the flow is from left to right here. We have two gears that are counter-rotating, and so they mesh in the center here. So essentially there's no path for the fluid to get through because these teeth are in contact. Now there's always a small leak path, but very, very low flow rate through there. However, as these gears rotate, they trap a volume of the liquid between the teeth and the outer housing. So all of these little pieces of fluid here are trapped and they're being moved in this direction to the discharge. And of course the same thing is happening at the top here. So this is a gear pump and it's positive displacement because each of these little volumes of fluid are being mechanically displaced from a low pressure region to a high pressure region. So that's a gear pump. So a lot of these are quite similar. This is called a screw pump. The inlet here is at the bottom, discharge out the top. The fluid comes in here and engages the flighting on the screws. And again, trapped volumes are moved from the low pressure up to the high pressure. These are quite common in especially larger refrigeration systems. A vane pump is very similar to a gear pump, only there's only one rotating element in it. And these vanes, which are these six plates here, go in and out of the rotating hub. So there's usually a spring in here or something forcing them against the outer housing. So as this rotates in the clockwise direction, fluid is trapped in there and it's mechanically pushed to the discharge. So here the flow is from right to left. So that's a vane pump. A three-lobe pump, again, is really very, very similar to a gear pump, just each of the gears only happens to have 3 teeth. This is sometimes also called a roots blower. So again, a trapped volume of liquid or vapor could be there is mechanically moved over to the high pressure side every time this thing turns. A circumferential piston pump is, again, the same principle. Volumes of liquid or vapor get trapped between the lobes of these counter-rotating shafts and moved around to the high pressure side. So a very similar type of operation. A flexible tube pump, also called a peristaltic pump, is our final example of positive displacement pumps. So in this picture, the thick black line here, that's actually the cross section of a rubber hose. So this hose heads off to do whatever. Fluid is coming in here. These rollers are turning, connected to this arm, and they pinch off the fluid and they trap a volume of fluid in there and transfer it around to the higher pressure side. So low pressure here, high pressure there. And there's lots of different designs of these, but the principle is all like this. Some of them have more than 2 rollers, maybe 3 or 4 rollers, but they provide a trapped volume of fluid by pinching this rubber or plastic hose as they move around. So one good thing about these peristaltic pumps or flexible tube pumps is there's really no leak path for the fluid to get out of that rubber tube. As long as the rubber tube doesn't break, there's no rotating shaft penetrating the pump housing or anything like that where there could be any leaks. So these are very popular in medical applications. So that's positive displacement pumps. Now we'll take a look at dynamic pumps. And dynamic pumps are good for moderate flow rates and moderate pressure increases. So sort of middle of the road in terms of flow rates and pressure increases. They do, however, often need priming. So if we're using a dynamic pump for liquid flow applications, then quite often if there's a vapor inside of there, they won't pump at all. So we need to open them up somehow and get liquid in there so they're liquid filled. So they're a little bit difficult to start under some circumstances. A nice feature of dynamic pumps is that the exit can be closed, and unless we leave it closed for a long time, there's not going to be any damage to the pump. And we'll see why that is when we look at the detailed construction of the inside of dynamic pumps. And these are by far the most common type of pump, particularly centrifugal or radial flow pumps, which is where we'll be spending most of our time. So here's a centrifugal pump or a radial flow dynamic pump. On the left side here, it's shown in cross section. So we have the suction pipe here. The fluid is coming into the suction pipe. But very soon after it starts to engage the impeller, which is this part, it turns and travels radially. So most of the time in this pump, the flow is moving radially from the center of rotation, which is here, out to the periphery. So this is called a radial flow or centrifugal pump. Notice there's a little bit of axial flow at the very beginning here just to get engaged with the impeller, but primarily it's traveling in the radial direction. So in the other view here, 90 degrees to our first view, we see the full impeller. So this is the impeller and it's turning, in this case, in the clockwise direction. And of course it has a bunch of vanes on it that guide the fluid from the suction side, which is the middle of this picture, out to the discharge side. And when the fluid comes off of the impeller, it's collected in the scroll and eventually makes its way to the discharge at point 2. So we're going to be doing quite a detailed analysis of the flow as it engages these impeller blades, and we're going to get performance equations for these types of pumps as we go forward. This is just an introduction to what they look like. So you can see here why in a centrifugal pump it's actually not that big a deal if the exit is closed off. This impeller spins but the fluid is not in a trapped volume. The pressure isn't going to go to extremely high values. It'll go up to some fairly moderate maximum and just stay there and not really damage anything. If we were to leave it like that for a long time, the fluid in here would certainly heat up, perhaps to dangerous levels. It would take a little while for that to happen. Now, in terms of pump classification, earlier when we were looking at centrifugal pumps, we saw that the pump curve was a very important performance characteristic of the centrifugal pump. It captured the performance of the pump very well. And the pump curve was a plot of the pump characteristics in terms of the pressure increase across the pump versus the flow rate through the pump. So we want to revisit that set of coordinates now that we've started to talk about different types of pumps. As we said when we were looking at these different types of pumps, positive displacement pumps tend to work well for low flow rates and high pressures. So positive displacement pumps we'll find work in that region of the delta P versus Q space. Centrifugal pumps are middle of the road. So moderate flows, moderate pressure increases, we would find centrifugal pumps being used. Axial flow pumps will be at higher flow rates and lower pressures. So we see positive displacement there, centrifugal pumps in the intermediate region, and axial flow pumps at the higher flow rate region. So in terms of pump performance characteristics, we've already taken a look at centrifugal pumps. So a pump curve for a centrifugal pump will generally look something like this. So if the flow rate is 0, there's some maximum pressure that they can produce at the discharge, given by that shutoff pressure or shutoff head. And as the flow increases through them, the pressure that they're able to produce drops off and drops off. So that's a typical pump curve for a centrifugal pump. For positive displacement pump, the pump curve is, to a first approximation, just a vertical line. And that's because each of these pump curves is drawn for a pump running at a particular speed. So if we have a positive displacement pump running at a particular speed, then the flow rate that it produces will be very, very constant because it's taking trapped volumes of liquid or vapor and transferring them over from the low pressure to the high pressure by direct mechanical displacement. And however fast that shaft is turning determines how many of those little volumes is being moved from low pressure to high pressure. So the flow rate that we're going to get is going to be very constant. In fact, that's one of the nice features of positive displacement pumps, is they can be used for metering. When we want to deliver a known amount of fluid or vapor, and we want that to happen regardless of what the back pressure is or the pressure increase across the pump, positive displacement pumps are very good at doing that because the pressure can change quite a bit and the flow rate really doesn't change because it's almost a vertical line. Now you'll observe from this little sketch that when the pressure increase gets high, the flow rate does eventually start to drop off. Well, that's because there is always a little bit of leakage back through a pump. So in the case of a positive displacement pump, if it's a gear pump for instance, this would be the flow that's leaking back around the gear teeth against the direction of flow, because we have very, very high pressure on the discharge, low pressure on the inlet. So that pressure difference is driving flow to leak back through any path it can find back from the discharge to the inlet. So that causes the flow to drop off a little bit as the pressure gets very, very high. Now the last one on here are axial flow pumps, and again they are used typically at very high flow rates and moderate pressure increases, and their pump curve sort of mimics a centrifugal pump fairly closely, but they tend to have a bit of a positive slope here before they reach a peak pressure, and then that starts to tail off much like centrifugal pumps. Next, we want to revisit the idea of pump efficiency and just define a couple of new terms that are in common use in the pump industry. So remember, this is our little schematic diagram for a pump. And we discussed earlier that the rate at which the pump does work on the fluid is the product of the volume flow rate through it and the pressure increase across the pump. So we call that W dot F, so the F standing for fluid. So the work rate done on the fluid is the pressure change across the pump times the volume flow rate through the pump. And of course this pressure change can be represented by a head, so rho g HQ. So that's the W dot F. Now of course the amount of work that we need to actually supply to the pump will be larger than this due to the inefficiencies that happen inside of the pump. So we connect a motor to this thing, and the rate at which work is done on the pump in the shaft is called W dot S, the shaft work. And so the efficiency of the pump is the rate at which work is actually being done on the fluid divided by the rate at which work is done on the pump. So that ratio W dot F to W dot S is the pump efficiency. Now each of these terms has a name that is quite common. The top one is called the water horsepower. Now it doesn't necessarily have to be water that's being pumped, and this work rate or power certainly doesn't have to be measured in horsepower, but it's still called the water horsepower. So that's the rate at which work is done actually on the fluid. And then in the denominator, the so-called shaft work is also often called the brake horsepower. So that's the rate at which work needs to be supplied to the pump. And again, it doesn't have to be in horsepower. More commonly these days it would be in kilowatts, but it's called the brake horsepower. So the ratio of the water horsepower to the brake horsepower is the pump efficiency. Every 100 units of work that come in here, perhaps only 70 of them actually are done on the fluid, and the rest is lost. So we want to talk about where those losses go. So the efficiency is the combined effect of three things in a pump. First one is the hydraulic efficiency. We spent quite a bit of time a few weeks ago looking at pipe friction. So that was energy losses in piping systems due to friction. So that's the friction in the fluid, the shear stresses at the wall, and turbulent losses inside of the fluid. Well, the same thing, of course, is happening as the fluid flows through the pump. There's fluid friction that is going to decrease the pump efficiency because some of the shaft work that is being done on the pump is going to be lost to those frictional forces. There are also other frictional forces that go into mechanical efficiency. There are bearings holding the shaft in position. There is typically a pump seal that is sealing the penetration where the shaft enters the housing, and there's lots of friction, or some friction at least, associated with those moving surfaces. So that's the mechanical efficiency associated with friction in the bearings and the seals. So notice both of those are really frictional effects that are decreasing the efficiency. The last one is called the volumetric efficiency, and this is due to leakage in the casing clearances. Now I talked about this a little bit in the context of positive displacement pumps, but of course it happens and even more in centrifugal pumps. So this is flow in the opposite direction to what we want. So the pump is increasing the pressure of the fluid, means the discharge is at a much higher pressure than the inlet, and that pressure difference can drive the flow in the opposite direction in the clearance spaces between the impeller and the casing. So that essentially means you need to pump the same fluid twice, and so that decreases the efficiency. The amount of fluid you're actually moving is less because a little bit of it is leaking backwards. So all of those things contribute to the pump efficiency.